The first question says, the dot plot below shows the distribution of the number of bedrooms in each of 21 apartments advertised for sale in a new high-rise apartment block. Then we have a dot plot, and question 1 said, the mode of the distribution is, and then we had a few options. So the trick with this one is knowing that mode is the most commonly occurring or the most often occurring observation. So which one of these occurs the most number of times? Well, it's as simple as looking at which one has the highest bar here, which one has the most number of dots, the most number of occurrences. And you can see that 1 occurred 1 extra time more than 3. So this one here is the most commonly occurring. It occurs the most number of times. So the answer is 1. Question 2 said the median of this distribution is. Okay, so median is the middle number when they're all in order. The middle. So there's 2 ways we could do this. We know that there are 21 in total. So remember the median is the n plus 1 over 2 th position. So we could say 21 plus 1 over 2, which is 22 over 2, or the 11th position in. Count in 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So one of these occurrences of 2 must be the median, which makes the answer B. The other way to work that out is to count from the bottom and the top, finding your way into the middle. A little bit like this is a stem and leaf plot. So we'd go from the bottom, from the top. So let's start with 1, 2, 3, 4, 5 from the bottom, 1, 2, 3, 4, 5 from the top, 1, 2, 3 from the bottom, 1, 2, 3 from the top, 1 from the bottom, 1 from the top, 1 from the bottom, 1 from the top. I get to that same point. It's that occurrence of 2, so the median of this data set is 2. Question 3 said, a student obtains a mark of 56 on a test for which the mean mark is 67. Okay, we've got a mean of 67 and a standard deviation of 10.2. The student's standardized mark, standard z-score, is closest to. So for this we need to use the formula for z-scores, which is z equals x minus the mean of x over the standard deviation of x. And this formula is found on the formula sheet at the back of the exam, but you can also grab it out of your textbook, or you should have it somewhere in your notes somewhere too. So our z-score is the x, the actual observed score, which in this case was 56, minus the mean, which in this case is 67, over the standard deviation, which is 10.2. So whack that into your calculator and you'll get negative 1.08. So the answer to question 3 is A. Question 4 said, the length of 3-month-old baby boys is approximately normally distributed, there's some keywords, with a mean of 61.1 and a standard deviation of 1.6. The percentage of 3-month-old baby boys with a length greater than 59.5 is closest to. So this to me, with these keywords here, sounds like one of these 68, 95, 99.7 rule questions. So we have a bell curve, an approximately normally distributed distribution, and the mean in the center is 61.1. And we're going to go standard deviations either side of 1.6 up and down. The key number that I'm looking for is 59.5. So before I figure out what 3 standard deviations up are, I'll figure out the ones 3 standard deviations below to save time and see if I can hit this 59.5 number. So first I put into my calculator 61.1 minus 1.6, which is this standard deviation, and I get 59.5. Aha! I've already hit my magic number. 59.5 is 1 standard deviation below. So if I'm dealing with 1 standard deviation below, I'm looking at the 68% rule. So I have 68% in the middle here. What I'm trying to find with this question is the percentage of boys with a length greater than this. So I want to know everything above that line. So there's a couple of ways I could work it out. Because I know there's 68% in the middle here, in this section there's 68, which means that in the 2 tails, the rest of the 100 minus 68, there must be 32 left over. So if there's 32 all up, splitting these in half, there must be 16% in that tail and 16% in that tail. So I could either say my 68% in the middle here plus this 16% on the other side, which would give me 84%. Another way of looking at it might be to say, well, I don't want this section. I want everything other than that section there. And I know this section is 16%. So 100, all of it, in other words, minus 16 would give me 84%. So either way, with both methods, I decide that this section here, this whole bit in there, must be 84%. Everything above 59.5 is 84% of the data. So my answer is D. Question 5 said, samples of jellyfish were selected from two different locations, A and B. The diameter in millimeters of each jellyfish was recorded and the resulting data is summarized in the box plots shown below. And now we have some side-by-side box plots. We've got location A and location B. Those labels on there are going to be quite important for the question. Which said, the percentage of jellyfish taken from location A with a diameter greater than 14 millimeters is closest to. Okay, so we need to find location A and we need to find the 14 millimeter mark. So this one here is location A. So we're only going to look at this. We're not going to look at location B for this question. We need to find the 14 millimeter mark. So we look at our scale along here. This line here is the 14 millimeter mark. And what do you know? It's the Q3 part of this box plot. So we're talking about the percentage of jellyfish that has a diameter greater than that point. So everything up here. Now, if we've got a box plot split into these four sections and the median is the middle, that's exactly halfway through the data, and these are the middle again, the Q1 and Q3 points are the middle again, halfway through the other halves, so to speak, then we can say that we've got a quarter in each of these sections. So there's 25% between the minimum and the Q1. There's 25% between the Q1 and the median, or the Q2. There's 25% in there between the median and the Q3. And there must be 25% in this chunk up here between the Q3 and the maximum. So the answer, the percentage of jellyfish taken with a diameter greater than 14, is 25%. The next question related to the same set of box plots, and it said, from the box plots, it can be concluded that the diameters of jellyfish taken from location A are generally similar to the diameters of the jellyfish taken from location B, less than the diameters of the jellyfish taken from location B and less variable, less than the diameters of the jellyfish taken from location B and more variable, greater than the diameters of the jellyfish taken from location B and less variable, greater than the diameters of the jellyfish taken from location B and more variable. So our options are talking about whether the diameters are less than or greater than, and whether they're less variable or more variable. So we're talking about location A and looking at comparing them to location B down here. So first of all, are the diameters and the variation of these two similar? They're not, so it's not going to be number A, letter A. If we have a look at the variableness of them, these ones are all bunched up. This box is quite skinny, meaning that the data is all in a clump around about this median in the middle. This box is wider along here, meaning it's more spread out. It's got more variation to the data. So it's going to be more variable. So I can rule out this one which says less variable, and I can rule out this one which says less variable. So it's not going to be one of those. Now we've got, are they generally less than the diameters of B or generally greater than the diameters of B? Well, here's A, and it's generally all in a lower part of this range. B's up here somewhere, between here and here, and A is lower. So A is generally less than B, and it's more spread out, more variable. So the answer is C. The diameters are less than the diameters of the jellyfish taken from location B and more variable. Now we have a scatter plot which relates to questions 7 and 8. The lengths and diameters in millimeters of a sample of jellyfish selected from another location were recorded and displayed in the scatter plot below. The least squares regression line for the data is shown, and that's this here. The length equals 3.5 plus 1.87 times the diameter, and the correlation coefficient for this linear regression is r equals 0.9034. Question 7 said, written as a percentage, the coefficient of determination is closest to. So coefficient of determination means r squared. We've been given the correlation coefficient, which is r. So all we need to do is take this number and square it. So put it into your calculator and have 0.9034 squared. The answer to that is 0.8161. Now, this answer here is trying to stumble you up by saying, just taking this number and saying, okay, rounding it to 3 decimal places, there's my answer. But they want this written as a percentage. So percent means per 100 divided by 100. So we need to move this decimal place 2 places. You could either type divided by 100 into your calculator, or you could do this little trick, 1, 2 jumps, and that's where I'm going to put the decimal place. So written as a percentage, this is actually 81.61, which rounding it up, I get to 81.6, making the answer C. Question 8 asked, from the equation of the least squares regression line, it can be concluded that for these jellyfish, on average, there is a 3.5 millimeter increase in diameter for each 1 millimeter increase in length, 3.5 millimeter increase in length for every 1 millimeter increase in diameter, and so on. So what this is asking us is looking at this equation, interpreting what it means, what this C and M part of our equation y equals mx plus c actually mean. Now the C, the part that's added on, is the y-intercept. And this here, a certain increase for each 1 millimeter increase in the other, is talking about the gradient. As one increases, how much does the other increase by? So our C is not part of this. We're talking about gradient. We want the M. Now here, which one of these two is times by the x, is times by the variable? 0.87 is times by the variable here, times by diameter. So this part is the M, and this part, 3.5, is the C, which means that 3.5 doesn't come into play. So I can get rid of that one and that one, because that's not talking about the M. The M is 0.87, so I don't know what this 4.37 business is about. We don't need that one either. So we only have 2 options left now, C and D. And this is talking about, it's flipping diameter and length. It's just trying to get you thinking about this. So 0.87 increase in diameter for every 1 millimeter increase in length, or a 0.87 increase in length for every 1 millimeter increase in diameter. So what our equation says is that length equals something that's happening every time we change this diameter. There's a 0.87 times the diameter. So what is happening to length is that every time we change the diameter by 1, we go up by this 0.87, because 0.87 times 1 is 0.87, and then 0.87 times 2, and 0.87 times 3. So every time we do something to diameter, length changes. So here there is a 0.87% increase in length for every 1 millimeter increase we do to the diameter. So the answer here is D, because this would be the other way around if our independent and dependent variables were flipped. If we had diameter equals something something times length, then this would be the correct answer. But in this case, we're talking about length increasing for every 1 millimeter increase in diameter. So the answer is D. Question 9 was about data transformations, and it said this: a student uses the following data to construct the scatter plot shown below. So here's our table of data, and here's the scatter plot that results. And as you can see, it follows a non-linear sort of trend. It's got this curve to it. To linearize the scatter plot, she applies a log y transformation. That is, a log transformation is applied to the y-axis scale. So we're doing log, and what we're doing it to is the y's, as opposed to doing it to the x's, which is something we could also do in transformations. She then fits a least squares regression line to the transformed data. With x as the independent variable, i.e. staying the same, the equation of this least squares regression line is closest to. So the trick to this question is enter this data into the lists of your calculator. So put x into list 1 and y into list 2. And then we want to transform this data by doing a log on the y's. So in a third list column, ask it to do the log of whatever this is, so list 2, or the log of y if you put that in there. And it will fill in these values in here for the log of this number. So we want the log of these numbers in a third column. Then we run a linear regression. So you say linreg a plus bx or ax plus b, what have you, on x versus this column. So you would say linreg L1 versus L3, or if you've named these, then you would put those names in there. So we get the linear regression of x versus our new column of log y's. And you'll be given something that looks like this. In the form y equals ax plus b, I get the variables a equals 0.23 and b equals 0.88, rounding up. So in y equals mx plus c, the c part here is 0.88 and the m part is 0.23. So instead of y we had log y, so that's what we need to phrase it as, which all of these have here. And then the part that's being times by the x is 0.23, and the part that's added on as a constant is 0.88. So where are those numbers? They're here. Here's 2.3 being times by the x and a constant of 0.88 being added on. The answer is D. Question 10 is a basic sort of a question, doesn't require doing any calculation, yet most of the students who took this exam in 2007 got this wrong. Only 37% of students got this right, so if you struggled with this one, don't worry, you're not the only one. This question said the relationship between the variables size of car and salary level is best displayed using one of the following. So what we need to look at here is the fact that these are both categorical variables. Size of car is categorical, that's a word, that's really obvious. Plus, it's also been put into 3 categories, 1, 2, 3, representing small, medium, and large. Salary level is also categorical because it's been put into these 3 categories, small, medium, and large, represented by the numbers 1, 2, and 3. So it's tempting to think it's numerical, but really we've just got 3 categories. If we did maths to those numbers, 1, 2, and 3, we wouldn't get any statistical information out of it because we haven't measured anything, we haven't counted anything, we're just looking at low, medium, and high. If we had the actual salary figures, then that would be numerical data, but putting it into 3 categories makes it clearly categorical. So for a scatter plot, you need numerical information. You need numerical down here and a numerical going up here, and you put dots. So it clearly can't be a scatter plot. A histogram is for numerical information as well. Remember, a bar chart like this has categorical, but it also has a frequency of occurrence. So histograms, where they're touching one another, is for numerical data. So it's not that one. Parallel box plots, again, we would need some numerical data to do something about that because we'd have to put the scale going along here, so it can't be parallel box plots. Back-to-back stem plots with data, numerical data coming out either side, again, we would need numerical data. So the only one that works here is a percentage segmented bar chart because we've got these 2 categorical variables. So a percentage segmented bar chart would look like this, with this being, low, medium, high, or small, medium, large for the cars, percentages of the response that we got back. This would work for 2 categorical variables. Now we have a time series plot showing the revenue from sales in dollars each month made by a Queensland souvenir shop over a 3-year period, and this will relate to 3 questions, 11, 12, and 13. Question 11 said, this time series plot indicates that over the 3-year period, revenue from sales each month showed no overall trend, no correlation, positive skew, an increasing trend only, or an increasing trend with seasonal variation. So let's rule these out one by one. First of all, no overall trend. Well, that doesn't seem right because there's a definite trend going on here. It's actually increasing up the page, and then there's these funny peaks as well. So it's not no overall trend. No correlation? Well, correlation doesn't really apply to a time series in this way. We're not really talking about how well does month correlate to revenue. So it's not going to be that one. A positive skew. Well, that would be if the numbers were all bunched up towards the negative. So it's definitely not that. And we don't really talk about skewness with time series plots anyway. So it's not that one. An increasing trend only, or an increasing trend with seasonal variation. There is an increasing trend. You can sort of see it's going up like this, but there are these peaks and they repeat at about the same time each year. See, this is around about the 12th month, this is around about the 24th month, and this is around about the 36th month. So that's probably going to go down there again like that at the start of the next year. So we do have this seasonal variation happening. So there's an increasing trend with seasonal variation, which means the answer is E. Question 12 was about a 3-median regression line, and 37% of students in 2007 got this right, so not a great deal. So if you struggled with this question, you're in good company. The question said a 3-median trend line, so a 3-median regression line, is fitted to this data, to this scatter plot. Its slope is closest to. Okay, so what's the first step for a 3-median regression line? We need to split it into 3 groups. Now, how many points have we got altogether? We've got 3 years, so there's 36 points here. So we've got 36, we'll put them in 3 groups of 12. 12, 12, 12. So after this 12th month here, that can be my first group, and after the 24 here, that can be my second group. Now I need to find the 3 median points in these, but I don't need to find the center one because all I'm doing is finding the slope. And remember, slope is determined by the far left-hand median and the right-hand median and the slope joining those two. So I just need to find those points. So I put my ruler on the page and I work out the median vertically and horizontally. So going up the page, the first point I hit is this one, these two at the same time, so that's number 1 and 2. Then I hit that one at 3, 4, 5, 6, and there's the 7th, and so on. Now where's the middle of 12 points? If I have 12 points in this group, I need to find the one that's 6.5 of the way through. Now the reason I don't choose the 6th point, which you would think 12 divided by 2, that's 6, that's halfway, it's not actually, because if we have 6 points lined up, for example 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Say we have data like that in a list and we're trying to find the median. We go 1, 2, 3 from the bottom, 1, 2, 3 from the top, 1, 2 from the bottom, 1, 2 from the top. It's halfway between 6 and 7. We're trying to balance an even number of points either side of this median. If I had chosen 6 for my median, that's not in the middle because I'd have 1, 2, 3, 4, 5 below it and 1, 2, 3, 4, 5, 6 above it. Another way to think of it is remember that n plus 1 over 2 th position? So in this case we have 12 points, so that's 12 plus 1 over 2, so that's 13 over 2, or the 6.5 th position. So we're going 6.5 of the way through this data. So there's 1 and 2, 3, 4, 5, 6. I want to split the 6th and the 7th. So going up the page, between those 2 points is where my median line is. And looking at this scale, looks like it goes up by thousands. So this is 1,000, 2,000, 3,000. And going across the page, which one do I hit? That one first, 2, 3, 4, 5, 6. Halfway between the 6th and the 7th is going to be there, which is at 6.5. So this median point here has the coordinates 6.5, comma, 3,000. Now, what about this one over on the right-hand side? The first point I hit going up the page is this one. Then I hit that one next, going up the page, and then that one, that's 3, 4, 5, 6. So going up the page between the 6th and the 7th puts me on this line here, which going across to the scale occurs at 5,000, 6,000, 7,000. Okay, and going across the page is nice and easy too, because being a time series, they're in order. So there's the first one, second one, third, fourth, fifth, sixth that I hit. So halfway between there and there, right smack on there is where my median point is, and that occurs at halfway between this dot, which is at 30, and this dot, which is at 31. So we've got 30.5. So the coordinates here are 30.5, 7,000. So now I need to find the slope joining those 2 points. So I've got 6.5, 3,000, and I've got 30.5, 7,000. So how do I find the slope between 2 points? y2 minus y1 over x2 minus x1, or rise over run. So let's do 7,000 minus 3,000 over 30.5 minus 6.5, which gives me 4,000 divided by 24, which is 166.7. So rounding that up, my slope is 167, which means that the answer to question 12 was C. And I don't need to do the rest of this 3 median business. I don't need to find the median of this middle section, put my ruler on these two and slide a third of the way towards it, because all I need to do is find the gradient. And even though these 2 points won't fall on the line, the gradient will be parallel, because these two are how we get the gradient. We put our ruler on these two, and then keeping the angle of the ruler the same, we slide towards that other one. So we determine our gradient from these two, and then we move towards where the line should be. So the gradient joining these two is going to be the same as the gradient of our 3 median line. The final question, 13, said this: the revenue from sales in dollars each month for the first year of a 3-year period is shown below. Month revenue. If this information is used to determine the seasonal index for each month, the seasonal index for September will be closest to. Okay, so where's September? That's here. What we're trying to find is what this number will be as a seasonal index. So how do we find their seasonal index? We're going to have to divide this number, 4597, by the average of all of these numbers. So how do you find the average, the mean? You add them up and divide by how many there are. So in your calculator, you put 1236 plus 1567 plus 1240 and so on, and just double check that you've entered them all correctly, and you should get 43,872. Then we divide by how many there are. There are 12, so we divide that by 12 and we get 3656. Now that's the average for the revenue each month. 4597 for September is greater than that. It's better than average. So our seasonal index should be 1 point something because it's above. So how do we find it? We take this number, 4597, and we divide it by the average for all of these, which is 3656, and you get 1.26. So the answer is E.